So today we will discuss what is linear regression, what are the aims or benefits that we want to achieve from implementing a linear regression model, and how to find the best fitting line, and we will go through a manually solved example. So what is linear regression? Linear regression is an approach of modeling data with a linear model. So if we have data that has the outcome variable and one or several independent covariates, we are trying to build a linear relationship between the outcome variable and the covariates or the covariate of interest. So basically we are fitting a linear model, and by linear model we don't always mean a line only. A line is just one type of a linear model, but we mean that the coefficients themselves are linear. So they are not squared, they're not raised to the power of 3 or 4, they're not square rooted, they're not, for example, themselves are an exponential of something else. So the coefficients in the model are linear themselves, but the model itself can have x, can have x squared, can have a square root of x, as long as the coefficient associated with that covariate is linear. So let's look into some data. So if we have a two-dimensional plot of y and one covariate x, and let's say our data is distributed this way, we can suspect from the way or the exploratory analysis that we perform by plotting the data that there is somehow a relationship between y and x. In this case, it seems that as x is increasing, y is also increasing. But this increase, of course, is not directly one-to-one. So we are aiming to find how to represent this increase or this relationship in the best manner. So we can fit a line and say that this line somehow represents the variability or the change in y associated with the change in x. But what about this line? And what about this line? So all of these are lines that cross through the data. Some of them intuitively cross better, but we will see how to do some mathematics to find actually the best fitting line. So eventually, this type of linear regression will yield us with some type of an equation that looks like this. So the outcome variable, y, is a function of the input variable, x in this case, plus an error. So if you notice, the error is coming from the fact that these points are not lying on these lines directly, but there are some distances, vertical distances, between this line and the point itself. And this is where the error comes from. So the error basically is we assume in the linear regression that it's completely random, so that we captured all what we can from the actual relationship in this function, and whatever is left is a random noise that we cannot forecast or predict. So what are the aims of doing a linear regression model? Why bother trying to fit a line through our data? Well, basically it helps us predict the output. So if we have values, for example, if this is our regression line and we have a value x1 that is representing the x variable, we can directly predict what y would it be, even though we would have an error, but we would know the mean or the average of what y should be. If we have another value of x, we can also predict another value of y, and so on. Also, we can forecast a trend. So this line, even though our data is captured, so let's say from here to here, in terms of the x variable and the y variable in our observation, we can still forecast beyond the boundaries of our data. So we can see that the slope is continuing from this side, so we can forecast how would it look in the future, or how would it look for x values that are outside our observations. So for example, if we are talking about an ice cream shop and our x variable represents the temperature, then we can forecast that as the temperature increases, for example, the sales will still increase. By knowing a few observations, we can predict some type of a relationship that we can forecast the trend of in the future. Also, we can quantify the causal effect of the relationship or the strength of that relationship. How much is y affected by x? So for example, if our regression line ended up looking something like this, we can say that there is a weak relationship between x and y, because as we see, as x is increasing, y is very barely increasing. Also, if we look at something like this, we can say that y is not really affected by x. For a specific value of x, y can be any value on this line. If we look at this line, for example, we can say that there is a strong linear relationship between y and x. because it seems like as x is increasing, y is also increasing by the similar rate or even a higher rate. And also it could be decreasing. So if x is increasing, y could be decreasing with a high trend also. So for example, if we're talking about the dose of the antibiotic in x and the remaining number of bacteria, alive bacteria, we can say that at dose 0, this is the number. As we increase the dose, it's decreasing by this much. So these are the three main benefits that we are trying to get from fitting a linear model into our data. Now to the big question, or the big elephant in the room, as they say, how to find the best fitting line. So we can fit a line like this, we can fit a line like this, or we can fit the blue line or the yellow line, and all of them are passing through the data, but some of them seem to fit the data better or fit the trend in the data better. Well, how can we do it mathematically? So it's not just an intuition and we select a line based on how we see it fitting the data. So let's first look at a single line. So what we know is that we talked about some error basically. So what we want to think about is a way to make these errors as small as possible. Because somehow when I make these errors as small as possible, it means that my line is actually passing through most of the data points or the observations. So I'm minimizing this error. So what is my error? My error is just the vertical distance between the observation and the prediction, and the prediction is represented by the line. So for example, for this point, let's say the error is E1, which is this vertical distance. For this point, it's E2. For this point, it's E3, and so on. So we have E4 and E5 and E6. For every observation, there is an error. So it seems like a good idea to sum these errors and try to minimize the sum. Because eventually, if I minimize this sum, I'm going to end up with a line that passes through most of the data. But think about one thing, we'll come across through a problem because some of these will cancel each other. So even though our line is not really passing through these points, but just because some of them are on the positive side of the line and some of them are on the negative side of the line, some of them, when we sum them, will cancel each other. So we cannot just work with the sum of the errors. We need somehow to make these errors all positive, so when we sum them, they don't cancel each other out. So there are two ways to do it. We can take the absolute value of them, or we can square them, because we know any number squared will be positive. And we choose to go with the squaring because it helps us in the arithmetics of finding the solution. And hence comes the idea of minimizing the sum of squared errors. So eventually we will square all these errors, so all of them will be positive. We will sum them and we will find the line that has the minimum sum of these squared errors. Because think about it, if my observations are very close to the line, once I square them, they will be even sometimes closer if it's less than 1, or they will be within a shorter distance of the line from a point that was far, and by squaring that distance, whether it was on the negative side or the positive side, it will become even further. So we're trying to minimize a sum of squared errors function. So let's go one step back. So our yi, which is one observation indicated by subscript I, is a function of xi, which is also one value of the independent variable x, plus an error associated with this. So for example, this point we called it 1. It will be y1 equals f of x1 plus the error 1. Now, if we don't want to think about the error, because really what we are trying to model is a relationship without the error itself, because the error, we said it's random. So we're talking about the expected value, which is a concept in statistics that is very close to the mean value. So the expected value of yi given, and this is given, xi, so if for a given x value, the expected value of y is this. And this is represented by f of x of I, which is the equation of this line. So now my error becomes yi, which is the actual position of the point, minus the expected value of the point, and this is going to give me this distance. And now if I want to talk about the equation of a line, in this case, we know that the line has an intercept. So the intercept is the value when your x is 0. So at x0 there's an intercept and there's a slope, which we call here beta. So with the intercept of alpha and the slope of beta, I can represent the equation of any line in the world. So what we can do here, we can say that the expected value of y given x equals f of x, which is alpha plus beta xi, where alpha is the intercept and beta is the slope of the line. So the slope of the line represents by how much is my line leaning upwards as I'm increasing my xi. So for example, for xi equals 1, it's going to be alpha plus b. For xi equals 2, it's going to be alpha plus 2b, 2 beta, and so on. Now we said minimize the squares of the errors. So what is my squared error? So my squared error is just the square of this, and it's going to be yi minus this, which is equal to that, all squared. And now if I just take the sum of all my squared errors, it's going to be the sum of this, and I distributed the negative sign over here, so it's minus alpha minus beta xi all squared. And this becomes my sum of squares function. So basically this is the function that we are trying to minimize to find the best fitting line, which is by solving for alpha and beta that would minimize the sum of squared errors. And we call this the sum of squared errors function. Now here comes the least squares estimator. We call it the least squares or sometimes the ordinary least squares because it's trying to minimize the squares of the errors. And there is another way, which is the maximum likelihood estimator, which is the MLE. And for the linear regression or the linear models, it's always gonna achieve the same solution as the OLS. And the maximum likelihood estimator uses more of statistics and probability, so it looks at the data, talking about the likelihood of seeing this data given that my coefficients alpha and beta are these values. So it's a different way to do it, but it achieves the same solution. So now, as we said in the previous slide, we're trying to minimize this sum of squares function and finding the alpha and beta that would minimize this. So we say that what is the alpha and beta that would minimize this argument. And what we can do, as you know from your calculus, you can take the derivative and make it equals to 0 to find the minimum point. But in this case, we have two variables, so it's not one variable. So what we do is we take the partial derivatives and we do the same thing. We just make the partial derivative equal to 0 and solve the equation. So to take the partial derivative of this, let's start with alpha. So it's basically going to be the derivative of this with respect to alpha. And if I take the derivative of this, basically, I'm doing the chain rule. So I'm taking the derivative of this term, which is going to be 2 times this term. Then I'm going to take the derivative of what's inside. And what's inside is minus alpha. So the derivative is minus 1, because everything else is constant with respect to alpha. So it's going to be a minus 2. The minus is coming from the minus 1 over here, and the 2 is coming from this 2 going down for whatever is in the parentheses. And I'm going to make this equals to 0. Now we go one step further and start removing the minus 2 because it doesn't make any difference to divide by minus 2 for both sides. So I'm going to lose it and I'm going to keep the 0 on the other side. Then I'm going to distribute my sum. So if I distribute my sum, it's going to go inside. So the sum of yi minus n alpha, and n here, it's because alpha doesn't have any subscripts, so it doesn't change. It's basically what we are trying to find as the coefficient. So if I put this sum next to the alpha, it's going to be alpha plus alpha plus alpha plus alpha n times. So it's basically n times alpha minus beta sum of xi. So xi has different values. If you remember, every observation had a different value for x. So I'm going to sum over all these x's. And this is supposedly equal to 0 to find the alpha that would minimize this equation. And now we go one further step and say that the sum of yi is basically n times the average of all the y's. If you're not convinced with this, try it out with 5 observations, for example. So if I take 5 random values and I sum them, I'm going to end up with a value. And if I take their average and multiply it by 5, it's going to be the same value. Because if you think about it, the average is just summing the values and dividing by their numbers. So if I take this number to the other side and multiply it by the average itself, it's going to give me a value equals to the sum. So this is going to be n y bar minus n alpha minus n beta x bar. And since I have an n in all these terms, and n is a constant, it's the number of observations, I can just lose the n and end with solving for alpha as alpha equals y bar minus beta x bar. I'm taking the n alpha to the other side and I'm dividing everything by n, I'm going to end up with this. The hat here says that this coefficient is estimated to reach the minimum sum of squares. So the alpha hat is my estimate for that coefficient of the linear model, and it equals to y bar minus beta x bar. Now if I do the same to find the value of beta, as you notice, beta is still here. So what we are trying to do is to find a solution for beta and then use both of these to solve a system of equation and find a value for alpha and beta that is independent of each other. So to do the same thing for beta, we take the partial derivative with respect to beta, and this time the 2 is also gonna come down, and in front of beta there is a minus and there is xi, so it's gonna be a minus 2, and the xi is still gonna be inside, but it's gonna be outside the parentheses, and I'm multiplying it by this term inside. And I'm gonna make this equal to 0, so I'm gonna take the negative 2 out, and I'm gonna end up with this. Now let me distribute my sum of xi, so I'm gonna end up with sum of xi yi minus alpha sum of xi, because sum of xi is still outside, minus beta sum of xi squared. So xi here and xi there, they're gonna be multiplied by each other, and it's gonna be sum of xi squared. So let's get more space and go into the next slide. So this is where we ended. And now, since I know alpha in terms of beta, we just solved for it in the previous slides, I'm going to replace alpha with the term that I solved for, which is the y bar minus beta x bar. So this is exactly this, except that we replaced the alpha with y bar minus beta x bar. And now let me do some distribution again. So sigma xi yi stays the same, minus y bar, which is this, multiplied by sum of xi, plus this minus and minus becomes a plus over here, so it's plus beta x bar is staying the same, sum of xi, and the last term is staying the same. Now let me do some regrouping. So if I take the sum of xi from the first two terms, it's going to be yi minus y bar, what's left. And if I take a minus beta for the second term, so I'm going to take the minus beta out, so it's going to be the sum of xi times xi, which is this term, minus x bar, which is this term. And the minus here is because we took minus beta outside. So now I can easily solve for beta by taking this to the other side and dividing by this term. So I'm going to end up with beta equals the sum of xi times yi minus y bar over the sum of xi times xi minus x bar, which is the average of the x's and the average of the y's. We can express it like this, but usually we express it with this way. And this makes our lives easier, as you will see in the next slide. So you might be wondering, where did the x bar come from in the numerator, and where did it come from in the denominator, since this is only xi. But if you want to convince yourself with it, just multiply this by each other, and multiply this by each other, and you will see that you will end up with two quantities that are equal. And since the results of these is equal, it means that these two terms are equal. So this is just another way that makes our life easier in representing it. So now we ended up with solving for the intercept, which is the alpha. And the alpha is going to look like this, the alpha hat. And we solved for the slope, which is the beta hat, and it's going to look like this. And as we said, this representation is also represented in another way, and we call this S of xy, and we call this S of xx. So S here represents the sum of squares. So in the first term here, it's xi minus x bar and yi minus y bar. Hence there's an x and there's a y. And here they're both x's. So this is xi minus x bar times xi minus x bar, which is just xi minus x bar squared. And if I take this term now and put it over here, my alpha hat is going to be y bar minus S of xy over S of xx times x bar. And with this, I know that the equation of my line is going to look like this, because it requires an intercept plus a beta hat or a slope that is multiplied by the independent variable. So now I have my expected value, or what we call yi hat, which is the estimate of any y observation. Now let's go into an example which will make us understand this a little more. So let's say we have 7 observation data. We have the x, which is the independent variable, and we have the y, which is the dependent variable. And let's envision it on this 2D plot. So our data would be in here. For example, the first point would be x equal 1 and y equal 2.1. The second point is going to be x equal 2 and y equal 3.9, and so on. So now we want to find the best fitting line that would fit through this data. To do this, we remember that we needed a few quantities. We first needed the average, the x bar, we needed the y bar, and we needed the SXY, and we needed the SXX. So let's do some calculations. So first, to get the average, we need to get the sum of the xi's. So let's sum all of these xi's together, and we will end up with 28. And to find the x bar, we just divide this 28 by the number of observations, which is 7, and we end up with 4. If we do the same for the yi's, we'll just sum these values together, and we will end up with a 57.5. And if we divide it by 7, we get y bar equals 8.21. And now, to get the sum of xx, or the sum of squares of xx, basically, what we need to do is just take this value, 1 minus the x bar, so it's 1 minus 4 squared, plus 2 minus 4 squared, plus 3 minus 4 squared, and so on. And I sum all of these sum of squares. And I'm going to end up with this number, and it's going to be 28. And if I do the same for SXY, so SXY is a little more complex arithmetically, but it's the same idea. So it's 1 minus 4 for the first term, and multiplied by 2.1 minus 8.21. For the second term, it's going to be 2 minus 4 times 3.9 minus 8.21. And I'm going to sum all of these terms together, and I'm going to end up with a 59.5. So now I have my 4 values over here, and if we remember, alpha hat equals y bar minus s of xy over s of xx times x bar. So it's if I just substitute the numbers, it's going to be minus 0.29. And my beta hat, if I substitute the numbers for sxy and sxx, it's going to be 2.125. So this tells me that I have the intercept and I have the slope of my line, so I can just fit the line directly. And if we look at this line, it seems that it fits the data perfectly. Its intercept is minus 0.29 and its slope is 2.125. And the beauty of having this line is I don't have to stick only to my observations. So let's say I want to know the value of when x is 2.5, what do I expect y to be? So if we go here to 2.5, I expect y to be somewhere around 5, for example. So with this, we completed the linear regression and we understand the least squares estimation method. And as we said, the method achieves the best fitting line solution similar to the maximum likelihood estimator, except that it's arithmetically or mathematically easier to implement. And in the next video, we're going to see how linear regression is done in R so we can solve more complex problems. If you like the video, please hit like and subscribe and share it with others to make them benefit from what we are learning. Thank you and good luck with your data analysis.